So I'm going to talk about this project that I've been doing last year in collaboration with Giuseppe, Juan, and Davide Galli at the University of Milan. And so I was involved in the NETKET project, as Giuseppe was saying at the beginning. And so this talk is about using NETKET to study this quantum spin system CAT. So just a second. That I see some background noise. Okay, here I am. So let's start from the method that we are using, and then I'm going to talk a little bit about the systems. And I guess all the method that has been more or less presented during the previous talks, but let me review those for really briefly. So we all know that we have these variational methods that can be used to tackle optimization problems, where we have functions that we want to optimize. And these functions depend on some relevant variables that encode some important features of the system that we are interested in. And then we have a set of parameters that are variational and that we can tune in such a way that that function gets to the minimum value, so the optimal value. And part of these, so the two components involved in the variational methods are, the first one is the determination of these optimized values. And the other part is also the choice of the parameterization. And there are a lot of work that has been done using in this topic. So starting from the analytical work done by Feynman for giving insights for the wave function in the superfluid helium type of systems. Then this was analytic work, but then this has become more computational, and so people have started introducing variational function to be tackled by a computational approach, either for bosons and fermions, and this goes back all the way to 1960, 1970. So it's a long story here, and like more recently, as we have seen in this conference, there are a lot of some different methods that can be introduced for like a better parameterization and a better representation of the wave function, in this case, in general, of a function that we want to optimize. And in this talk, I'm going to focus on the neural network quantum states. So the method that we used in the project was the variational Monte Carlo, so an approximated computational method, and the goal was to estimate basically ground state properties of a quantum many-body system. And so as we already seen about the variational Monte Carlo method, there is, first of all, a parameterization of the wave function that is needed to specify the state that we are considering. So once we fix a certain basis state, then we have a wave function that depends on certain parameter W. And then the basis of the basic foundation of this method is the variational principle of quantum mechanics, in which the Monte Carlo sampling procedure is used to compute the variational energy, so this observable that we want to optimize in order to get as close as possible to the ground state of the system, and therefore to have an estimate of the energy ground state, and also of the other relevant observables that can be used to describe the ground state properties. So here is, in a nutshell, some of the more analytic formulas that we can use for the variational Monte Carlo method, in which instead of, so we have some these local observables that can be used to estimate stochastically the relevant observables, and then specifically for the optimization of the parameters in our project, we use the stochastic reconfiguration method that we already have seen in this conference previous talks. And so the update of the parameters depends on a certain learning rate, which is fixed, and then depends in this more complicated way on the gradient of the wave function, so of the energy of the of the system. And therefore, this is how we update our parameters. So I'm not going to go in the details of this, since we have already mentioned this. So here is where the neural network quantum states come into play, in the sense that we have specified all the details of the method, but not yet how we define this wave function, depending on those parameters. So as we know, like usually this can has been approached in a like more physics inspired way. So for example, using a Jasper wave function on like ansatses that consider 2-point correlations and similar, also more complicated things. So, but the idea is that there was a physics inspired approach. But the other approach that has been introduced, starting from the work by Giuseppe and Mattias in 2017, is to use this machine learning inspired ansatz for the wave function. So using artificial neural network to represent a wave function, since we all know that the wave function is a function of a lot of variables, then it's convenient to have a compact representation of that. And so the more compact and the more powerful representation we can have, the better it is to get insights on the physics that we are interested in at the end of the day. So we are using this RBM that we have seen all the way back in this conference, in which we consider as, so the relevant parameters, just let me recall that the relevant parameters in the RBM is alpha, which is just the ratio between the number of hidden variables and the number of visible variables, which encodes the expressivity of the RBM, because the more hidden units you have, the more, in principle, the more expressive the machine is, since we can encode more correlations, more indirect correlations between the visible spins. And the power of the artificial neural network ansatz is exactly that we can encode correlations between the different variables in a compact and like powerful way. So the neural network quantum state, as we know, is just identifying the wave function with the RBM probability. And so once you have a machine, then the learning procedure here is exactly the variational Monte Carlo optimization that I mentioned before. So since we have seen the net part, now we can go to the ket part. And so which model we studied in this project. We just focused on the Heisenberg model, so here you can see the Hamiltonian that we all know, and the lattice that we consider to study this Hamiltonian on is the bidimensional honeycomb lattice. So here you can see the unit cell, the fundamental cell, and so to expand a little bit more on the model, we consider a positive coupling. So we are interested in the antiferromagnetic version of the Heisenberg model, and then the sum runs just over the nearest neighbors pairs, and we consider 1/2 particles, spin 1/2 particles. So the system is SU2 invariant, and so this is like a bigger representation of the lattice that we are considering. And so it is known that the ground state of in general of a bidimensional bipartite lattice is the classical Nit state with quantum fluctuation. So the classical Nit state is just the state in which the spins are anti-aligned, and the quantum nil state introduces some fluctuations in this alignment between the spins, and the result of this is that the antiferromagnetic long-range order that is occurring in the ground state is reduced by the presence of these fluctuations. So why we decided to study this model? Because this is a very important prototypical model in condensed matter physics, and also paves the way to understand some specific materials and some specific phenomena. But also this is the first step to study the J1, J2 model that we have seen in other talks by like for example, by Kenny. So this is like a first step to then go to the problem of frustrated models where the magnetic structure of the ground state is not just this simple anti-aligned or more or less anti-aligned structure, but more complicated magnetic structures. And this is interesting also from a practical point of view to get to study the high temperature superconductivity. And so what are we interested in about this system are, as I mentioned, the energy of the ground state. So we want to see if the neural network quantum state ansatz is able to get us to the ground state energy of the system, but also we are interested in the magnetic structure of the ground state, which is the other relevant observables, which is a way more difficult to study. And what we use as an observable to quantify the magnetic order is just the spin-spin correlation function, because in the long distance limit, sorry, in the large distance limit is just the magnetization. So how do we put all of these together? So since this is a NETKET talk, I'm gonna tell a little bit how I run my simulations using this software. So I use the NETKET and also contributed a little bit on this on the development of this, especially for the lattice part. And what we wanted to do, as I just said, is the variational learning of the neural network quantum state to get to the ground state of the Heisenberg model. And these simulations, as you will see in a second, are like very easy in a sense that it's easy to code using NETKET, but they are also very computational demanding, especially considering larger and larger lattices. It becomes like more and more expensive. So just a brief overview of NETKET. So as it was said before, the 2.0 version was based on a C++ core, and now it's been ported to a Python version. But still, like, this is kind of the structure that was there, at least in the version 2.0. And so there are a lot of tools to define the quantum model. Then you have another layers that is used to define the machine architecture, so the ansatz, and also all the tools that you can use for the optimization. And then there are finally some more machine learning related tools, in the sense that you have to specify also how to learn and how to train your machine. And also there are some exact method for benchmarking. So it's a pretty like various and interesting architecture here. But all of this is very simple to use, in the sense that this was more or less the backbone of the simulation that I was running. So you just have to define all that you need and then run the optimization in the last line. Therefore, you can specify, you know, like the lattice that we are using, the Hilbert space of the spins, then the operators, so the Hamiltonian that we are considering, and we considered the Hamiltonian with the Marshall transformation in order to have like to avoid the sign problem, and also the answer that you can choose for the RBM. So there are several RBM versions, and we in the software, and we use a symmetric RBM and RBM in the sense that we can encode all the lattice symmetries in the ansatz, and this allows us to reduce the number of parameters that are needed, and so to simplify a little bit the optimization. And then just like initializing the parameters and setting everything that you need for the optimization, and then running. So it's quite straightforward. In 30 lines of code, you have everything you need, and then you just wait until it runs. And what are the results that we obtained? So for the Heisenberg model, we studied the energy per site, varying the number of, so the parameter alpha, so the RBM expressivity, and we ran simulations for different lattices, starting from 3x3 and all the way to 8x8 lattices. And also we compared the results that we obtained in the variational Monte Carlo setting with exact quantum Monte Carlo simulation that we ran using the ALPS library. And so these are the results for the 3x3, 4x4, 6x6, and 8x8 lattices. And we can see that as we increase the expressivity, the energy is getting closer to the exact value. And also the relative error with, with respect to the SSE, so the quantum Monte Carlo simulation, is better than previous VMC outcomes, as the one we mentioned here. So, I mean, this was more or less expected because the ansatz was promising given all the results and everything that we have seen in the previous days. But also we wanted to go a little bit deeper, and so we wanted to study also the ground state, the magnetic nature of the ground state, and therefore we run this finite size scaling analysis for the Heisenberg model, and this is what we get. So the energy scaling and the correlation function scaling confirms the antiferromagnetic long range order that we knew was there from the theoretical point of view. And then we ran these simulations more in a deeper, to study in a deeper way the correlations. So we studied separately the correlations between the on the XY plane and on the Z direction. And we see these fairly marked asymmetry between the Z and the XY correlations. And these suggest the presence of a bias in the RBM wave function ansatz. So we wanted to study these more in a deeper way. And therefore we run the same exact simulations, but using the XY model, because since the spins tend to align on the XY plane, as we saw in the slide before, so the magnetization on the XY plane is higher. So we focused on that plane to see what is going on and to see what is the correlation in that case. So we selected this model and we ran the same simulation. So we see like even more accurate results for the energy accuracy and the finite size scaling for energy. And then what happens for the Z and XY correlations, we can see that there is a great accordance, the great agreement between our simulations and the SSE, so the exact simulations, both for the XY projection and for the Z projection of the correlations. And therefore, it appears that having an ansatz with the correct spin symmetry helps considerably in the precision and in the accuracy of the correlation. So this is more or less the work we did. And I just want to highlight the fact that this is the first time that there was this bias occurrence in the RBM ansatz, and therefore these cause for a deeper understanding of these neural network quantum states ansatz, specifically for these RBM. So there are a lot of some different steps that can be done like on these lines, but I guess the most important thing, at least in my opinion, is to go deeper in this bias that we have seen and understand where is this coming from, because this helps to having more insights on the method itself. So thank you all for your attention.